Welcome once again to Simpkins Physics Corner. It's a little chilly in the Simpkins Physics Corner. It's like 10 degrees outside, but it's warm in the corner. So today we're going to talk about the conditions for rotational equilibrium with this problem. So let's go ahead and take a look at the problem, and we'll talk about the concepts underlying the problem. A uniform wooden beam with a mass of 20 kilograms, so I'll go ahead and label the beam here, mass 20 kilograms, extends horizontally from a wall as shown. A support cable of negligible mass extends from the far end of the beam to the wall, forming a 40-degree angle with the beam. The beam has a sign with mass of 5 kilograms hanging from the end of it. Question A says find the tension in the cable, so that would be asking us to find this overall Ft equals, I'm not sure. That helps support the beam and the sign, and then it says find the horizontal and vertical components of the force that the wall exerts on the beam. So we're looking for Fx of the wall, and we assume that there'd be some kind of force of friction here, Fy of the beam there. All right, so at first glance, this problem seems kind of easy, but there's a lot involved here. So the first thing we need to understand is how is this sign hung up? Well, we can always kind of assume for these problems that there's some kind of hinge, and in fact, you always, when you're talking about forces and torques, this is a new idea for this problem, you have to set the rotational axis. Where are we going to set our center of rotation, our rotational axis? We're going to set it here at the wall because it's convenient, because we know the length of, or we can use the length of the beam in the various positionings here in order to go off of this reference frame here. And plus, just think about it practically. Let's say someone came in and snipped the cable, right? You can imagine that this, if the cable is supporting a lot of weight, that this whole thing would rotate and come tumbling down. And so the center of mass here, the center of mass of this beam would kind of rotate downward if we were to cut this cable. Now, since the center of mass has the potential to move and it's not moving, we can assume that there's no translational motion, which means the first condition we can say for sure is that sigma F equals 0. We know that the net forces must all add up to 0 because this object's center of mass would be accelerating if the forces were not balanced, right? If I were to cut this cable, now that force is non-existent, the center of mass would move. Since there's the potential for that center of mass to move, we have to say, hey, if it's not, the forces must be balanced. The second thing we can say is, since this thing would also rotate if we cut that string, and it's not rotating, we say it's in rotational equilibrium, so we can say the second condition is that the sum of all the torques, sigma tau, would be equal to 0. So we can say that all the torques must add up to 0, and these are the two essential ideas we need to understand as we crack into this problem. So let's just think first, what kinds of things are exerting force, and then we'll say, hey, which of those forces are exerting torques? So of course, the center of mass is going to have the force of gravity acting on it, so I'll call this Fg, we'll call it the beam, since it's the wooden beam. The beam has mass, and gravity's going to be pulling down. Gravity happens to act on the center of mass of all objects, so that's where the force of gravity is going to be exerted on this beam. We also, of course, this sign would be pulling down, and you can get into technicalities. You say, well, the force of gravity here on the sign would be equal to the tension force since it's in equilibrium, but that tension force would be equal to the force of gravity. So you can see very quickly from this that the sign will be exerting a force of gravity. So I'll call it Fg of the sign, not the sign trig function, but Fg, the force of gravity that this sign is exerting, pulling down on this beam. And of course, the force of tension, you can see that it has both an upward and a leftward component, which is going to be important. So I'll call this Fty, and then of course it would have some kind of I'll draw it down here, Ftx, which we'll get to later. So now we've considered the forces, and now let's consider the torques. If this is our chosen rotational axis, then what things would cause this beam to want to experience a rotational type of motion? What things would be exerting a torque? Well, of course, this force of gravity of the beam would be exerting a torque because it is a certain distance from a lever arm. Torque is defined as a force applied at a certain lever arm distance from the center of rotation, and we can say either the perpendicular component of the force, or sometimes people throw a sine theta at the end of that. So in order for something to exert torque, it needs a force, and it needs to be not at the axis of rotation that we've chosen. So that qualifies. So let's go ahead and write our sigma torque expression as we gather these up. There's going to be a torque from the beam because it has a force and it has a certain lever arm distance. There's also going to be a torque from the sign. See, the sign is exerting a force downward. There's going to be a torque from the sign. And then, of course, there'll also be a torque from the tension. Now you can imagine these downward forces, or you can't really say these downward forces are going to cause a torque in this direction, the clockwise direction. And of course upward forces then would cause a tendency of a torque in a counterclockwise direction. So I'll go ahead and write torque of the tension in the cable equals 0. Of course, we would keep in mind this guy is in the opposite direction of the others. And to indicate that, we can definitely say that the torque that the beam exerts plus the torque that the sine exerts must be equal to the torque that the force of tension is exerting. All right, and we can say that because we know that this guy is opposite, equal, and opposite would add up to 0. All right, so that's kind of how we start that one. Now, torque is involved with force and a lever arm, so let's go ahead and write that expression. The force on the beam, of course, would be the force of gravity on the beam. I'll just write Fg of the beam. And that would be times the distance. Now, we don't get the length of the beam, which is kind of sucky, but let's call the whole beam length L, and of course the center of mass of a uniform mass beam would be right in the middle, 1/2 of L. So I'll call that 1/2 of L. Plus, let's see, torque from the sine, that would be the force of gravity on the sine, the force, times the lever arm. In this case, it's all the way out the end. So the lever arm, the distance from the rotation point is L. That's going to equal the torque of the tension. And I'm going to be really careful about this. We know that the force of tension, while it's in this weird direction, the x component of that isn't going to exert any torque. Because since the lever arm is in this direction and the FTX is in that direction, and they're parallel, that means that it's not going to exert any torque. Consider trying to take a bicycle wheel and pushing on the outer edge of a bicycle wheel like this. It wouldn't cause it to spin. It wouldn't cause a change in its angular velocity. So this is actually the only force that's going to matter here is our Fty, of course, times also the radius L. So here's where we got to grind some algebra. We got to do a little bit of work, and we can go ahead and do that. Fg beam. Let's go ahead and do that. So I'll just write it over here. Fg beam. Of course, we know force of gravity is always calculated by mass times gravitational acceleration. So since the beam has a mass of 20 kilograms and a gravitational acceleration here, we can assume we're on Earth, is 20 times 9.8 would get us our force. So we have 196 newtons. Sorry, forgot the 6. Let's do the same thing, similar process for Fg of the sine. All right, of course, sing, that's fun. Oh, I can sing as well. But that would be mg. All right, and so we have 5 kilograms, 9.8 here. That would get us, what, 4.9? Usually we get that answer a lot. Not 49. Okay, that's why you do the math, folks. So let's go ahead and plug these in here. We have Fg of the beam is 196, so 196 newtons times 1/2 L plus 49 newtons times L equals Fty times L. Oh my goodness. Sometimes you don't even need the length, because if we're careful, look, this term has an L, this term has an L, that term has an L. Only if every term has an L may you cancel that on all the sides. So we can actually just eliminate the length there because we're working on the same beam. It's the same L across there. Don't forget the 1/2 though, so half of 96 will get you 98 newtons plus 49 newtons equals, let's see here, we're going to go to Fty. Now, here we go, Fty. We don't know the force of tension, but we can write an expression for it. Ft, and since this is this side, the vertical side, and that would correspond to this side of the triangle, relative to the angle we're given, the 40 degrees, this side we would call opposite, this side we would call hypotenuse. Opposite and hypotenuse by SOHCAHTOA would tell us to use the sine function, and so we could say Fty is equal to Ft sine of theta. And what you see here is that now we know enough stuff to find the force of tension on the string. And in fact, now we have solved for part A. So for part A, you would do Ft equals 98 plus 49. So that gets us 147 newtons. Divided by, see we have the sine of theta multiplied by Ft. So we have to divide both sides by sine of 40. And that would get us 147 over sine of 40. Make sure you're in degree mode to get the right answer. And that would get us a force of tension of 229 newtons if I round it with some sig figs there. So we've accomplished part A. It says find the tension in the cable. And we did that by leveraging our knowledge of torques. We know that since we are in rotational equilibrium, the torques must be balanced. So we set the total torque equal to 0. We figured out which torques were canceling each other out, if you will, or working against one another. We see that the torque from the beam and the torque from the sine are working against the torque from the cable. So we set that equation up, did some algebra, got our answer. Sweet. Now last part, find the horizontal and vertical components of the force that the wall exerts on the wooden beam. Of course, right? There's always more. There's always more to these problems. Over here, let's talk about a couple of things. Since we are in rotational equilibrium and the center of mass is not at the center of rotation, we can say that the forces must all be balanced. As we wrote, the sigma F is equal to 0. So for part 1 here, I'm going to look at all the up and down forces. So let's see, we have force of gravity of the beam, force of gravity of the sine. Those are both downward forces. And we have Fty, and we have Fy of the wall, which is what it's asking us to find. So I'm going to set upward equal to positive. So Fy of the wall plus Fy of tension equals, right, those are the two upward forces. They have to add up to the same total force as Fg of the beam plus Fg of the sine. Okay, so Fy of the wall is what we're solving for. Fy wall equals, let's see, Fg beam was 196, okay, plus Fg of the sine, which was 49, minus Fyt. Now, we know Ft is 229, so if I want to find the y component, I can do 229 sine of 40. And whatever I get from this should get me the y component of the force of the wall. So 196 plus 49 minus 229 sine of 40. And good news, we have an answer that kind of makes sense, 97.8 newtons. Of course, it needs to be an upward force because we can imagine the wall would be kind of helping it stay up either by friction or by some kind of hinge that's pushing up on that part of the beam. Right? If you had a bunch of stuff hanging over here and you didn't have something pushing up over here, it would maybe cause it to rotate. Okay, so that's the Fy, the y component. It says find that. So we've got that part. We can check that off. Then it says find the horizontal component. Well, this one's pretty straightforward, pretty easy. I might even let you do it, but since I have a little bit of room right here down at the bottom, what we can say here is that the x component, the wall pushing this way, is going to be equal to whatever forces are pulling this way to the left. Oh, only the cable's pulling to the left. So what we can say is Ftx of the wall is equal to Ftx of the cable. All right. Maybe I should just call it Fx wall. There's not really tension in the wall. It kind of sounds weird. Okay. But of course, you could just go ahead and solve for that. That would be the Ftx, because we already know the tension in the cable, it would just be 229 cosine of 40. And your final answer, we're almost there. I'm so excited. And we're not under 10 minutes, but we're under 15 minutes anyway. 175.4 newtons. All right. So there you go. The big points of this problem are because our center of mass is here and our rotational axis is here, and we know that we're in equilibrium, we're in rotational equilibrium, and we're in translational equilibrium. We can set the sigma F equal to 0 by translational equilibrium. We can set the sigma torque equal to 0 by rotational equilibrium. Now, did I get a bit messy with dropping off my meters, newton meters? Yeah, a little bit, but we got the answer out of here. The thing you just have to keep in mind is if you had an actual value for meters, that would work out for your newton meters. But you can see the L's canceled on all of those. So happy physicsing. Thanks for joining the Simpkins Physics Corner. And my students tell me I need to say, be sure to like and subscribe, leave a comment, and tune in next time. Yeah, all that nonsense. Whatever, I'm just here to teach people physics, so I hope you learned something.